Good day, sir. We are from Group 5, Fantastic 4. First, let us introduce ourselves. My name is Felicia.
I'm Jenki.
I'm Shendaryn.
I'm Yoven.
Before we start, do you know that the cement industry accounts for approximately 8% of global carbon dioxide emissions? Replacement of this with CNT-based composites will significantly decrease global annual emissions of carbon dioxide to help mitigate climate change. With that in mind, Jenki will start off our presentation for today about the application of carbon nanotubes in construction.
Now I'm going to present for the properties of carbon nanotubes. Physical properties of CNTs were mostly derived from base material which is graphene. It involved dense packing arrangement of carbon atoms in a regular sp2 pattern, and CNT is explicitly distinct in the cylinder form fabricated of swirled-up graphene thick sheet. Besides, CNTs have outstanding mechanical, thermal, electrical, and optical properties. Moreover, they have high angle proportion that are perfect for long and persistent detecting. Their high surface region can be misused for storing materials to make half-breed useful materials. CNTs are additionally known to display ballistic conductivity, and last but not least, CNT filaments are receptive to elastic, compressive, flexural, and torsional strain. Next, we are coming for the synthesis of CNT. There are several methods for synthesis of CNTs. First of all, with the chemical vapor deposition method, which vaporized reactants react chemically and form nanomaterial product that deposited in substrate. Hydrocarbon gas is pumped into the quartz tube, which undergoes pyrolysis reaction and form vapor carbon atoms. These carbon atoms bind to the substrate and join to each other by van der Waals force of attraction and grow as multi-wall carbon nanotubes. Second method is electric arc discharge method, which is also known as plasma arcing method. Electrodes strike each other to produce electric arc, and energy produced in it transfer an ionized anode to produce carbon ions, which move towards, get reduced, deposited, and grow as CNTs on cathode. As CNTs grow, anode becomes shorter, but electrodes are adjusted to maintain at fixed gap. If proper cooling of electrodes achieved, uniform deposition of CNTs are formed on cathode, which achieved by inert gas maintained at proper pressure. Lastly, here we go for a laser ablation method, which is also we call it as physical vapor deposition method, a technique which a material can be vaporized into gaseous form, then deposited on surface of substrate. Graphite target, which placed at center of quartz chamber, is vaporized by either continuous laser source or pulse laser source. Vaporized target atoms sweep toward cool copper collector, then deposited and grown as CNTs on collector. For last step of all methods, obtained CNTs are further purified to pure form of CNTs. Now I would like to pass to Felicia for her part.
Thank you, Jenki. Let me begin by explaining the roles of materials for its application. All carbon nanotubes are expected to be very good thermal conductors along the tube, exhibiting a property known as ballistic conduction, but also good insulators laterally to the tube axis. The temperature stability of CNTs is established to be up to 2800 degrees Celsius in vacuum and about 750 degrees Celsius in air. CNTs have been shown to exhibit superconductivity below 253 degrees Celsius. This is due to its exotic strengths, already heralded for their unparalleled strength and unique ability to adopt the electrical properties of either semiconductors or perfect metals. In addition, the strong in-plane graphitic carbon-carbon bonds make them exceptionally strong and stiff against axial strains. The almost zero in-plane thermal expansion but large interface expansion of single-wall nanotubes implies strong in-plane coupling and high flexibility against non-axial strains. Moving on to tensile strength and elasticity, CNTs are the strongest and stiffest materials on Earth in terms of tensile strength, elastic modulus, and yield strength. This strength results from the covalent sp2 bonds formed between individual carbon atoms. The carbon atoms of a single sheet graphite form a planar of honeycomb lattice, in which each atom is connected via a strong chemical bond to three neighboring atoms. Moreover, CNTs have high flexibility, and its microstructure shape as tubes is capable of bending in circles and forming bridges crossing the micro and nano cracks developed in the cement composites, which in turn increases the tensile strength of the cement composites. It is expected that CNTs, when added to concrete, will increase the compression strength beyond 200 megapascal thus allowing the construction of mile-high skyscrapers. In short, CNTs can reduce the occurrence of cracks, decrease porosity, and improve mechanical properties, thus extending the cement durability. I will now pass to Shendaryn to elaborate further on the challenges and recommendations of the materials. Thank you.
Thank you, Felicia. Hello, my name is Shendaryn, and today I will be presenting on the challenges of using carbon nanotubes in cement for construction applications and some recommendations to these obstacles. Firstly, due to the low solubility and hydrophobicity of carbon nanotubes, a lack of uniform dispersion is observed as CNT is added into cement paste. The poor dispersion is a result of the large surface area to volume ratio of CNT, where there is a strong van der Waals forces between CNTs that makes it difficult for them to disperse homogeneously. Next, as CNT is added into cement paste to overcome its brittle nature, large cost is incurred to prepare the concrete using CNTs. Due to the low dispersion of CNT, more CNT is needed in the cement paste and thus increases the cost. Due to the van der Waals forces, CNT tend to form agglomerates and bundles. These agglomerates function as local defects and thus inhibits the ability to support load transfer and mitigate the development of cracks. To overcome the problem of agglomerates, application of ultrasonication is suggested to agitate the CNT in cement paste. The application of ultrasonication is used in combination with either treatment of CNTs with group functionalizing agents or with addition of dispersing agents to improve dispersion of CNT in cement. Next, to tackle the problem of poor dispersion, silica fume is added to enhance the interfacial interaction between CNTs and hydration products due to their high pozzolanic activity. The pozzolanic activity is a measure for the degree of reaction over time. Additionally, silica fume could be intermixed with agglomerated CNTs to mechanically separate CNTs into dispersed fibers to further improve its dispersion. To lower the cost, it is recommended to apply direct synthesis of CNT on cement particles. As Jen Khee has mentioned, CNTs can be synthesized directly on the surface of clinker particles by thermal CVD. To add on to that, this method reduces the number of stages of composite fabrication that summarizes CNT synthesis, purification, and pre-treatment to only one stage. That is all from me, and I'll pass it to Yoven to continue the presentation. Thank you.
Thank you, Shen, for your insights. Recently, the World Economic Forum and Scientific American magazine have listed the top 10 emerging technologies of 2020, with one of them being low carbon cement that can help combat climate change. Meanwhile, a variety of lower carbon approaches are being pursued, with some already in practice. To list a few examples, firstly, low carbon technology. Solidia, a concrete technology company, has developed a novel form of concrete that reduces the overall carbon footprint by up to 70%. In a normal cement manufacture, process emissions come from the breakdown of limestone into lime and carbon dioxide, while Solidia cement is actually a non-hydraulic cement composed of minerals containing less lime than the minerals that compose traditional cement. Since less lime is required per unit of cement, less limestone needs to be calcinated, and this reduces process emissions by 30%. Moreover, ordinary concrete cures by reacting with water over the course of several weeks. However, in contrast, Solidia concrete reacts with the carbon dioxide molecules within a water CO2 solution and cures just in 24 hours. Next, the carbon capture and storage CCS technology. It is a technology that reduces large emissions of carbon dioxide, and it comprises a capture element, a transport element, and a storage element. Norsum, a leading Norwegian supplier of cement, has a vision of zero emissions from concrete, seen in a life cycle perspective by 2030. This vision will be realized through the development of new types of cement and by increasing the percentage of alternative fuels and carbon capture in cement production. And basically for the CCS technology, carbon dioxide will be transported by ship from the capture plant to an offshore facility for temporary storage. CO2 will then be transported via a pipeline to a subsea formation for storage. And lastly, bacteria in concrete formulation. North Carolina-based company Biomason employs bacteria to grow a durable cement in ambient temperatures, producing building materials without emitting any greenhouse gases and without any depletion of non-renewable resources. The nutrients and minerals required to grow the bricks are actually globally abundant renewable resources and may be also extracted from industrial waste streams, making this mode of brick production even more ecological beneficial. And this process also takes only less than 3 days in ambient temperatures. And that's all from us. Thank you. Before we end our presentation, the future is uncertain, but the end is always near.